Alright guys, in this video we're going to talk about how buffer solution works when you add acid. This is a question from slides number 22, and we solved the question A and B in our lecture. And for A, pH value for this buffer solution is 4.74. And for B, if you add a little bit of strong base, the pH value will increase slightly to 4.82. But as you can see, the buffer solution can maintain the pH value at the similar level. In question C, we're going to see how the buffer solution works if you add a little bit of strong acid, hydrochloric acid in this case. Here's what we need to do. In order to solve this problem, you have to do the stoichiometry calculation to find out the new concentration of conjugate acid and conjugate base after you add 0.01 mole of the hydrochloric acid. So let's do this step by step. First step is stoichiometry calculation. Because this is we are adding strong acid, so it will react with the conjugate base, acetate. Okay. To generate the conjugate acid, acetic acid, and the other product would be just chloride itself. Now, before reaction and the change, and after reaction. Okay, so here is the chart that we need to finish. Before the reaction, the concentration of this conjugate base is 0.1 mole per liter. Let me erase this. 0.10 mole per liter. And the concentration of the hydrochloric acid would be the mole number, 0.01 mole, divided by the volume, which is 1 liter in this case. Okay, so I got 0.01 mole. For the conjugate acid, the concentration of this acid is 0.10 mole per liter. Okay, so as you can see, because hydrochloric acid is a limiting reagent, so the change would be the concentration of the hydrochloric acid. Alright, so these are the change for the two reactants, and here you are going to generate 0.01 mole per liter of this acetic acid. Now after reaction, the concentration of the conjugate base would be 0.10 mole per liter minus 0.01 mole per liter. I got 0.09 mole per liter, and this is 0. And for the acid, 0.10 mole per liter plus 0.01 mole per liter, and that is 0.11 mole per liter. Okay, so this is a stoichiometry calculation for you to find out the new concentrations of the conjugate acid and the conjugate base. Now what's next? The second step is to use the IC chart, okay, to find out the new pH value from this buffer solution. Here's the equation that we need to use: CH3COOH. Okay. In water, equilibrium generate the conjugate base and hydronium. Okay. Alright, IC chart, initial concentration, change, and equilibrium concentration. Since we've already found out the new concentration of the conjugate acid and the conjugate base, these are the data that we need to use for this IC chart. Conjugate acid, 0.11 mole per liter. Conjugate base, initial concentration of conjugate base, 0.09 mole per liter. Hydronium, 0. The change, we don't know how much dissociated, so negative X, X, and X here. So equilibrium concentration, 0.11 minus X, 0.09 plus x and x. Alright, so the next thing is we need to solve x. So we need to use Ka value. Ka value for this acetic acid has been given, and that is 1.8 times 10 to the negative 5. Okay, and that equals to, based on what we have in this IC chart, that is 0.09 mole per liter plus x times x divided by the 0.11 minus x. And because x is very small, so we can assume that 0.09 plus x is 0.09 itself times x divided by the 0.11. Because x is small, 0.11 minus x is about 0.11 m itself. So if you solve x, that is 2.2 times 10 to the negative 5 mole per liter. Alright, so this is x, and based on our IC chart, x is the concentration of hydronium. So if you take the negative logarithm of x, that's going to be the pH value of this new buffer, of this buffer solution after you add that amount of hydrochloric acid. So step 3, pH value equals to negative logarithm of 2.2 times 10 to the negative 5 mole per liter. And my calculation is 4.66. Okay. So as you can see, that again, the buffer solution worked because before you add the hydrochloric acid, pH value is 4.74, and you add a little bit of hydrochloric acid, pH value decreased a little bit, but not that much. Okay, so this is how the buffer solution works. Of course, the last step is to check whether our assumption is good or not. So you use 2.2 times 10 to the negative 5 mole per liter, this is x, divided by the initial concentration of the conjugate acid, 0.11 mole per liter, times 100%. My calculation is 0.02%, which is much less than 5%. So our assumption is good, and this is the right pH value for this buffer solution after it absorbs 0.01 mole of hydrochloric acid. I hope this video can show you how the buffer solution absorbs the strong acid. Let me know if you have any questions.